All right, so picture this. You're out camping, stars are out, got a nice campfire going. You're just kind of gazing into those flames, mesmerized with them.
Yeah, I know the feeling.
But have you ever stopped to think, like, what's actually going on in there? Like the science behind those dancing
Oh,
flames?
absolutely. There's a whole world of chemistry and physics happening right before your eyes.
Totally. And today we're going to do a deep dive into exactly that, the science of flames.
Love it.
All thanks to some really interesting combustion research you sent over.
Yeah, this one was fascinating.
It focuses on this cool experiment with a burning liquid, and honestly, the findings are kind of surprising.
I think people are going to be really intrigued by this one.
I think so too.
Yeah.
Like, did you know the color of a flame can actually tell you how hot it is?
It's true.
Or that understanding how flames behave
Hmm.
can be used to, like, solve crimes.
Oh, yeah, fire forensics is a whole fascinating field.
It really is.
Yeah.
Okay, so let's get this deep dive burning.
Sounds good. Flames are like a mini window into some really complex scientific principles.
Okay, so let's talk about this experiment. What are we actually looking at here?
So imagine a controlled environment, right? Totally safe. And we're burning a liquid fuel. Could be something like ethanol
Okay.
or like isopropanol, stuff you might even have at home.
Yeah.
And the experiment is all about carefully measuring the height of the flame
Okay.
and really paying attention to its color.
Okay, so we're watching liquid burn. Why are those two things, the height and the color, so important?
Because they're like a secret code, a visual language that tells us what's happening during combustion. The height of the flame can give us clues about how quickly the fuel is burning and how much energy it's releasing.
Oh, interesting.
And the color, well, that's like a built-in temperature gauge for the flame.
That's so cool. I remember reading about that, like different colors meaning different temperatures.
Exactly.
Can you break that down for us?
Absolutely. Imagine a brilliant blue flame, super vibrant. That's the sign of complete combustion.
Really?
It means there's plenty of oxygen for the fuel to burn efficiently.
Oh, I see.
And because it's burning so cleanly, it burns super hot.
So blue flames are the hottest.
Oh, yeah, they really are. Now, picture those like yellow or orange flames, the kind you see in a campfire.
Yeah.
Those are cooler, and they tell a different story. That's incomplete combustion.
What does incomplete combustion mean?
It means there's not enough oxygen for all the fuel to burn up completely. And when that happens, you get soot,
Soot.
those tiny carbon particles. And they glow yellow or orange in the heat.
Gotcha. So that's why a campfire often has those flickering yellow flames. It's all about the oxygen.
Precisely. And sometimes you'll even see like red or white tips at the edges of a flame. Those are the cooler zones where combustion isn't as intense.
This is making me realize how much we take flames for granted. It's so much more than just fire. But let's rewind a bit. What's actually happening at like a molecular level when something burns?
Well, at its core, combustion is a chemical reaction, right? It's all about fuel reacting with oxygen. And in our case, the fuel is that liquid we're burning. Now, here's a key point, especially for liquids. It's called vaporization.
Vaporization. You mean the liquid has to turn into a gas before it can actually burn?
You got it. It's the vapor, the gaseous form of the fuel, that actually mixes with the oxygen in the air and ignites.
Okay, that makes sense. And this is making me think back to high school chemistry, like the laws of thermodynamics.
Yeah.
Do those apply here?
They're totally relevant here. The first law of thermodynamics tells us energy can't be created or destroyed, only transformed. So the energy stored in the fuel doesn't just disappear.
Right.
It transforms into that heat and light we see in the flames.
So the energy changes form, but it doesn't just vanish. What about the second law? Doesn't that have something to do with entropy?
You're right. The second law is all about entropy, which is basically a measure of disorder or randomness. And it says that in a closed system, entropy always increases.
Okay, so how does that apply to, our burning liquid?
Even though the energy from the fuel is transforming into heat and light, some of it inevitably escapes into the surroundings as heat. And this increases the overall entropy of the system.
So it's not really lost, it just spreads out and becomes less organized.
Exactly. And this leads us to another important concept, enthalpy of combustion.
Enthalpy. Yeah, that rings a bell. I'm not sure from where, though.
Enthalpy of combustion basically tells you how much heat is released when a specific amount of fuel burns completely. The higher the enthalpy, the more energy is released and the bigger and hotter the flame will be.
Oh, I see.
So like propane has a really high enthalpy of combustion, which is why it gives off so much heat compared to something like wood.
Wow. Okay, so we've got this chemical reaction happening, energy transforming, and this enthalpy thing driving the intensity of the flame.
Yeah.
It's all starting to make sense.
Great.
But how does the heat from the flame actually travel? Like, how does it affect what's around it?
That's a great question. And there are three main ways heat can travel: conduction, convection, and radiation.
Okay, let's break those down. Conduction, what's that all about?
Conduction is heat transfer through direct contact. So like when you touch a hot pan, the heat flows directly from the pan to your hand. In our experiment, conduction is happening within the flame itself and between the container holding the liquid and the surrounding air.
Okay, got it. What about convection?
Convection is heat transfer through the movement of fluids, like liquids or gases. Have you ever seen those rising currents of hot air above a flame?
Oh, yeah, totally.
That's convection in action. As the flame heats the air around it, that air becomes less dense and rises, which pulls in cooler air from below. And that creates those mesmerizing movements you see in a flame.
So convection's kind of like keeping the flame alive, bringing in that fresh oxygen it needs. What about radiation?
Radiation is heat transfer through electromagnetic waves, like light or infrared. It's how you feel the warmth of a fire, even if you're not actually touching the flames.
Ah, okay. So all three of those heat transfer things are happening at the same time around our burning liquid.
Absolutely. Conduction within the flame and the container, convection creating those rising currents, and radiation sending out waves of heat everywhere. It's a pretty dynamic system.
It really is. We've covered so much already, like from that chemical reaction to how heat travels. But I'm still curious about flame height. Like, what makes one flame shoot higher than another?
Great question. Remember how we talked about vaporization being crucial for liquids?
Yeah. Yeah, the liquid turning into gas to burn.
Exactly. The rate at which a liquid vaporizes plays a huge role in how high that flame gets. The faster it turns to gas, the more fuel there is to burn. And more fuel generally means a taller flame.
Makes sense. So it's almost like adding more fuel to a bonfire,
Mm.
more fuel, higher flames.
Aha, exactly. But there's another super important factor: oxygen. Remember how we talked about incomplete combustion happening when there's not enough oxygen?
Yeah, those yellow, sooty flames.
Right. If there isn't enough oxygen, even if you have tons of vaporized fuel, the flame will be stifled.
So it's like a balancing act between fuel vaporization and oxygen. What about all the flickering and dancing? Like, why don't flames just stay still?
Well, a flame is always responding to what's happening around it. The flickering and dancing are mainly due to those convection currents we talked about. That hot air rising and cooler air rushing in creates turbulence, and that makes the flame move and change shape.
Wow, it's like an ever-changing piece of art, shaped
Yeah,
by these invisible forces.
I like that. And remember, as the fuel burns up, the rate of combustion changes. That also affects the flame's size and how it behaves.
This is really eye-opening. We've learned so much about flames, but I feel like we've only just scratched the surface.
We've got a lot more ground to cover.
I'm ready. We're going to take a quick break, but we'll be right back to delve even deeper into the science of flames. Stay tuned.
Welcome back. Ready to keep exploring those fiery mysteries.
Oh, absolutely. Before the break, we were talking about how the color of a flame is like a built-in thermometer.
Yeah.
But how do scientists actually measure the temperature of a flame? You can't just, like, stick a thermometer in there.
You're right, a regular thermometer would melt in an instant. But scientists have some pretty cool tools up their sleeves. One way is by using a thermal imaging camera.
Oh, yeah. I've seen those, like, firefighters use them to see through smoke.
Exactly, they use them to find hot spots and stuff. Thermal cameras work by detecting infrared radiation, which, remember, everything gives off, but hotter objects emit more of it.
Oh, right, right.
So the camera uses this radiation to create an image that basically shows you the temperature of everything in the frame.
So, like, different colors on the image mean different temperatures,
Yeah.
and they can pinpoint the hottest parts of the flame.
Exactly. And here's something interesting. The hottest part is usually near the base of the flame, where the fuel and oxygen first mix and, things really get going.
Makes sense. It's like the heart of the fire.
I like that. Now, if you want to get even more precise with temperature, we can bring in some physics.
Uh-oh, physics.
Don't worry, it's not too complicated. We can use Planck's law and Wien's displacement law.
Oh, yeah, those names ring a bell from, like, forever ago, but I'm a little fuzzy on the details.
No worries, it's been a while for me too. Planck's law basically says that all objects give off electromagnetic radiation, and the intensity and wavelength of that radiation depends on the object's temperature. So hotter objects emit more radiation, and the radiation shifts towards shorter wavelengths as the temperature goes up.
Okay, so, like, a cooler object might emit mostly infrared, which we feel is heat, But a much hotter object would give off visible light, like the glow of a flame.
You got it. And that's where Wien's displacement law comes in. It basically says that you can actually figure out the temperature of an object just by looking at the color of the light it's emitting.
Whoa, so like analyzing the color of the flame can actually tell us its temperature.
Exactly. It's pretty cool, right?
Yeah. It's crazy how something as simple as a flame is connected to all these, like, universal physics laws.
I know, right? It really makes you appreciate the complexity of the world around us.
It does. Speaking of the world around us, let's talk about some real-world stuff. You mentioned fire forensics earlier.
Oh, yeah, that's a fascinating field. Basically, these investigators use their knowledge of how fire works to, figure out how fires started.
Like, they're like fire detectives.
Uh-huh, yeah. They look at burn patterns, the color and height of the flames, whether there's soot, all sorts of
Like,
clues.
instead of fingerprints, they're looking for clues in the flames.
Exactly. And this knowledge is also really important for safety, like when you're handling flammable liquids.
Yeah, like if you know how easily something can catch fire, you can create safer ways to store it and prevent accidents.
Exactly. And think about all the things we use every day that rely on combustion.
Cars, planes.
Exactly. Internal combustion engines, the ones that power most vehicles, are basically controlled explosions, turning chemical energy into movement. And understanding combustion helps engineers design those engines to be more efficient and less polluting.
It's crazy to think that a simple experiment, like the one we're talking about, can teach us so much about these things.
It really shows how science and engineering work together. And this knowledge applies to so many areas, like, designing heating systems for our homes or even creating materials that can withstand super high temperatures.
This is really making me see flames in a whole new light. They're not just sources of warmth, they're like these amazing tools for innovation.
I love that perspective.
Hmm.
So, as we wrap up this part of our deep dive, it's important to remember that we've only scratched the surface of combustion. There's a whole lot more to uncover.
I'm excited to keep learning. This whole thing is making me think about things like fireplaces and wood stoves. Like, if we apply what we've learned about how flames work, could we make those systems more efficient? Better for the environment?
Absolutely. Understanding how different fuels burn, the role of oxygen, and how heat moves around can lead to amazing new technologies. Like, imagine a fireplace that gives you more warmth with less wood, which means less waste and pollution.
That would be awesome. Like, cozy nights by the fire, but you know you're not harming the planet.
Exactly. We could even design the combustion chamber to distribute heat better, making the whole system even more effective. It's all about using fire smarter and in a way that's good for the planet.
It's like turning a fireplace into a high-tech heating machine.
Uh-huh, exactly. And this kind of thinking can be applied to so many things. Designing better car engines, creating new ways to generate energy from renewable fuels. The possibilities are endless.
It's amazing how understanding something as basic as a flame can lead to so much innovation.
It really shows that science is all around us. By being curious and asking questions, we can unlock so much potential and shape a better future.
That's so true. It feels like we've taken a deep dive into a flame and come out with this whole new understanding of science and its impact on our world.
I love that. And we've only just begun to explore the fascinating world of combustion. There's still so much more to learn and discover.
I'm already looking forward to our next deep dive. But before we wrap up, any final thoughts for our listeners?
I'd say embrace your curiosity. Observe the world around you, ask questions, and never stop exploring. You never know what amazing discoveries are waiting for you.
That's great advice. So to all our listeners, keep that curiosity burning and keep those questions coming. We'll catch you on our next deep dive into the wonders of science. Thanks for joining us. So welcome back to the deep dive. It's wild how much we've uncovered about something as like basic as a flame.
Yeah, it's been a really cool journey. We've covered so much from the chemistry to fire forensics and even making engines better.
Right before the break, we were talking about those fire investigators, the ones who solve mysteries using flames.
Oh yeah, the fire detectives.
Do you have any like really interesting cases where they were key to solving the whole thing?
Well, there are so many cases where understanding flames helped investigators. One that really stands out, though, involves a nightclub fire. It was a really tragic situation. The fire spread so fast, and unfortunately, a lot of people lost their lives. At first, everyone thought it was an accident, but the fire investigators, they were really thorough. They looked at everything, like, the burn patterns, how the flames spread, the smoke, and all those clues pointed to one thing: arson.
Oh, wow.
Yeah, it turns out someone had intentionally started the fire using an accelerant. The investigator's analysis, all that science, helped catch the person responsible.
Wow, that's a powerful example of how important that work is. It makes you think.
It really does. It shows how the science of flames can, make a real difference in the world. It's not just theoretical.
Yeah. This whole deep dive has got me thinking about fireplaces. Like, those cozy wood-burning ones?
Yeah.
Could we use what we've learned about flames to make them better? Like, more efficient, less smoke, better for the environment.
Oh, absolutely. If we really understand how different fuels burn, the importance of oxygen, and how heat moves, we can come up with some awesome innovations. Like, what if you had a fireplace that gave off way more heat but used way less wood, less pollution, more sustainable?
Yeah, exactly. Cozy nights by the fire without all the guilt.
Exactly. And we could even design the inside of the fireplace, the part where the fire burns, to spread the heat more evenly throughout the room, make it even more efficient. It's all about using fire in a smarter way.
It's like taking something as simple as a fireplace and making it super high-tech.
Yeah.
And
And this kind of thinking can be applied to a lot of other technologies too. Like, think about designing better engines for cars and planes, or even finding new ways to create energy using fuels that don't pollute.
this whole deep dive has been a real eye-opener. It feels like we've looked right into the heart of a flame and come out with this, like, brand new understanding of how science shapes the world around us.
And we've only just scratched the surface. There's so much more to learn about combustion. It's a huge field.
I'm already looking forward to our next deep dive. But before we wrap things up, any last words of wisdom for our listeners?
I think the biggest takeaway is to stay curious. Look around you, notice things, ask questions, and just keep exploring. You never know what amazing things you'll discover.
That's great advice. So to all our listeners out there, keep that fire of curiosity burning and don't be afraid to ask questions. We'll see you on our next deep dive into the fascinating world of science.
Thanks for listening.